Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to look at how our idealized kinetic gas can move through space. So when we're looking at how a gas moves through space, one of their biggest features is that they like to spread out. Again, this was one of our immediate definitions of a gas, is it tends to spread out to fill whatever container it's put inside. Now, there are several different terms we use to describe the movement of gas molecules. So we're going to be looking at two specifically. So the first of which is one you're probably familiar with, and this is the idea of diffusion. So if I have two different gases, and let's say I separate them by a barrier. So all of my hydrogen's on the left, all my nitrogen's on the right. If I remove that barrier, then what happens is the gases diffuse into the space held by somebody else. And one of the important features is that hydrogen doesn't really care whether it's surrounded by nitrogen or hydrogen, so one place is as good as the other. So they tend to move through random movement into each other's spaces. And they'll do this till they eventually reach an evenly mixed form. And one way to think about this is they'll reach the point at which just as much hydrogen is moving to the right as it is to the left. This stands in a mild contrast to effusion. So for effusion, you can imagine having a container full of one or more gases, and then it's sitting next to a vacuum. So this could be just an empty container. And then I poke a hole in the wall. Oh no, gases immediately move to the right, because here's the thing, they want to spread out. And there's no gases to move to the left, so everybody moves into the vacuum. And as they're identical, if I'm looking at one individual molecule, when it's moving either into a vacuum or to a space occupied by another gas, those are pretty much the same thing to this idealized gas. It doesn't care who it's surrounded by. So as a result, rates of effusion and diffusion should both be identical. And it turns out you can actually measure the rate of diffusion as 1 over the square root of the molecular, as related to 1 over the square root of the molecular weight. The exact proportionality will depend upon the temperature. So what this is often more important for us is if I'm looking at the rates of effusion or diffusion of two gases compared to each other. So let's say I have that mixture of hydrogen and nitrogen, and I want to know who's going to fill this vacuum space first, because that will make a big difference if there's something on the other side. Will it immediately react with the explosive hydrogen, or will it be inert to nice neutral nitrogen? And it turns out we can find the ratio of these rates based on the ratio of the square root of the molecular weights. Does this look familiar? And it turns out that this is because these rates are based on the speed of the gas. Yep, it turns out that the rates of effusion and diffusion are going to be proportional to the speed of the gas. The faster the gas, the faster it will diffuse. So if I'm looking at which one of these will effuse faster into a vacuum, it turns out that lo and behold, it's going to be the lighter gas. Because a lighter gas, so if I have a very small number down here, will tend to give me a very large rate, again, due to this inverse relationship. So hydrogen will fill up that vacuum far faster than the nitrogen, because as we saw previously, being the lighter gas, it will be the faster gas. And this is really important for any number of chemical phenomena when you're looking at how gases will move through a body or through a reactive chemical system. So next time, we're going to be looking a little bit more at how we can accurately predict the other physical macroscopic properties of a gas. Specifically, we're going to take a look in much more detail at the mess that is pressure. Until then, take care.